Hello, and welcome to Functional and Logic Programming course. My name is Dmitry Soshnikov, and let me begin by telling you a few words about myself. I'm cloud developer advocate at Microsoft. Before that, for 2 years, I was software engineer and data scientist working on artificial intelligence and machine learning projects with big European companies. And before that, I was technical evangelist for 10 years. The main thing that I like doing is getting people excited about technology, and in particular, young people and students. I also teach in a few universities in Moscow, in Moscow Institute of Physics and Technology, in Higher School of Economics, and in Moscow Aviation Institute, where I teach courses related to functional programming, logic programming, and artificial intelligence. I also have a number of online courses, and the one that you are watching now is one of them. Another thing that I like doing, I like to think how to get children excited about technology and about programming. I have a daughter who is now 16, and it's always my pleasure to see how she likes doing things by herself related to computer science. She's also interested in art, and that's why I try to explore the intersection between art and technology myself. And if you want to see some of the works that I'm doing, welcome to my website to learn more. I'm also an author of a few books. One of them is the first book in Russian on functional programming using F#, and another one on logic programming. So that's why I'm now I will be telling you about those subjects, because that's something I like, something I wrote books about, something I like teaching. And without further ado, let's begin the first lecture, which is Introduction to Functional Programming. So the first question you might have is, why do we want to learn programming again? Because probably you've learned programming in school, you've learned programming in the beginning of your studies in university, and you know how to do that, right? You know what programming is all about. However, why do you need to learn it? It turns out that there are different ways you can reason about programming. You can reason about telling computer how to do things. And the traditional way, called imperative way, is not the only one. And arguably, it's not even the best one. So, for example, imagine that the programs can look completely different. For example, the program that you see on this slide, you can probably figure out what it means just by looking at the name of the function, fact, but you probably have very little idea how you can define factorial without any loops, without any traditional variables, by just combining some strange functions together. So this is the answers on functional programming. Functional programming is when you think about program as a composition of simpler functions. One more example. Imagine you want to do symbolic differentiation. Symbolic differentiation follows quite simple rules, but still, to develop the symbolic differentiator, you would need to define trees, expression trees, operations on expression trees, and that would be pretty tedious. Now, imagine if somebody told you that you can just define the rules of differentiation as simple rules, like this, like in the program on the slide, and then the computer would figure out how to differentiate expressions by itself. So, in fact, what you are seeing here is the program in a programming language called Prolog, which does symbolic differentiation. You see just a few lines of code which completely resemble the definition, allow computer to figure out the algorithm and actually do this thing. So that's what we will be learning how to do, how to think about programming differently, so that we can approach some tasks and solve them with more efficiency and with more beauty. Why is it important? Because the more ways you see of looking at the problem, the better you are able to solve this problem. And we are going to see during this course 2 more ways at looking at computations. And that's important. Let's start with some history of computations, how computers came to be. You probably think that computers appeared sometime in the middle of 20th century, but that is not the case. In fact, the first idea of computer probably is attributed to Charles Babbage in 1822 when he built the difference engine. So the idea of difference engine was to be able to compute certain polynomials, because polynomials were important in calculating trajectories and coordinates of planets, and people used to do those calculations by hand. And Charles Babbage thought, how can he automate this process? In fact, there were some tools which helped people to do calculations, like arithmometers, but they required some manual work. And Charles Babbage tried to put those things together into a machine which is somehow programmable. In fact, the idea of programming something came about the same time with different kind of machines. First of all, sewing machines, which try to make different patterns on fabric by using perforated cards. Perforated card program the machine like the way it should combine the threads into the pattern, and that was kind of the idea of programming which was at that time. Another example is the company called IBM. You probably know it quite well. It's one of the biggest software and hardware companies now. It started with it appeared actually before computers. So the first project IBM was involved in is United States Census, when you need to collect a lot of data from different people. The idea was that people would provide data in form of punch cards, and the machine would process this data automatically. So the way the computations were done at that time is by using punch cards or certain devices which change the behavior of the system. Unfortunately, Charles Babbage was unable to build his computer because it was too technically, it required too high precision. It was too technically advanced. And in fact, even later attempts to build mechanical computers failed. Konrad Zuse is probably the one who built the first computer in 1938, and it is called Z3, the first working computer. Before that, he had the previous version called Z1, which was mechanical and which did not work reliably. So as soon as people started using electronic components such as relays, computers became actually useful and could do some useful things. So if the computers looked like that, how would you program computers? The way you program computers, initially, as I mentioned, it was using some punch cards or some hardware switches, which directly influenced how computations went. At a later time, people thought about storing the program in the same place with data, in memory, which is so-called von Neumann architecture. So in von Neumann architecture, the program would be just a sequence of numbers, machine codes, which are stored in memory. And of course, it's not easy to develop things using machine codes, and to memorize them, people started putting some abbreviations, some English words for machine codes, and that's how assembly language appeared. In assembly language, if you wanted to compute something like 2x plus 1, you need a sequence of commands, like take the value of x from memory, multiply it by 2, add 1, and store the result somewhere. And that was pretty tedious. So at some point, people thought that it would be more convenient to delegate the process of those simple steps to the computer, so that a person would be able to write a mathematical expression like 2x plus 1, and the computer would convert it into machine code or into assembly language. And that's how high-level programming languages appeared. The first one of those was Fortran, developed by John Backus. And Fortran stands for formula translator, so that was the main thing that it could do, translate formula into simple commands. But also, in addition to formula, it included some basic computational constructions like loops and conditional operators. In fact, the idea of those was developed during Charles Babbage times by Ada Lovelace. So that's how programming languages came about. They were some simplification for machine codes. So the idea of any traditional programming language is to be able to describe a program into a sequence of very simple elementary steps called algorithm, which would be understandable by computer. And the design of the language, therefore, resembles the inner working of the computer, which has memory and where different operators change memory into different states. Of course, after Fortran, there were many other programming languages like the ones that you know, C, C#, C++, Python, Java, and so on. But all those languages were pretty similar. Of course, they have their own beauty and their own benefits, but the main programming model is the same. You need to decompose the program into a sequence of steps which change memory. There are some really interesting languages, though, which are called esoteric programming languages because they don't look familiar, they don't look traditional. One of them is, for example, brainfuck. Brainfuck is the language which has only, I think, 5 simple commands. And with those 5 simple commands, you can develop any algorithm. However, the idea of brainfuck is also the same. You have memory, you can change this memory by commands to achieve certain results, even though the language looks quite different. One more esoteric language is called Romeo. The idea of Romeo language is opposite to brainfuck. It tried to be as verbose as possible. So this program tries to print hello world. In fact, not the whole hello world, but just a few first letters, because the program is written as a play. And the play tells what you need to do with registers, what you need to do with certain pieces of memory. But still, the idea, the semantics of the language is the same, even though the syntax is different. However, if you look into esoteric programming languages, you might think that this is also one of them. This is a language called FP. In fact, this language is totally different from the ones we saw before. So how it appeared? Initially, when John Backus created Fortran, he was awarded Turing Award for that. Turing Award is one of the biggest awards in computer science, and if somebody is awarded Turing Award, he has to give the open lecture. And during his open lecture, John Backus said that it probably was a mistake creating Fortran, and instead programming should look different. Programming should be used on sound mathematical foundation. And he proposed a language called FP, which stands for functional programming. And that is exactly the language that I showed you on the page before. You can probably again guess what this program does, but you would definitely not be able to understand why you need to underline one, why you need different kind of stars and composition operators. So it might look like it's not easy to develop things using this language. But in fact, the main problem comes from the fact that the language is different in a sense that it approaches problem from the different standpoint. But FP was not the first functional programming language. It was not the first one where the ideas of functional programming were proposed. In fact, the first language which was partly functional is Lisp. Lisp is multi-purpose language. It's not purely functional. It contains different aspects. It contains some features from traditional programming and a lot of functional features. But the main idea behind Lisp is based on lambda-calculus, a mathematical theory developed by Alonzo Church in the beginning of 20th century. Alonzo Church was not thinking about programming. He was thinking about developing the foundation of mathematics. In a slightly different way, not based on mathematical logic, but based on some formal symbolic systems. This symbolic system was called lambda-calculus, and it turned out that Church invented the definition of algorithm by proposing this lambda-calculus, because lambda-calculus describes exactly the set of computable functions. And based on this idea of algorithm, it's not very easy, but you can very beautifully build a programming language, and that is what functional programming is all about: building the programming language on top of very beautiful mathematical theory called lambda-calculus. So what is the main difference between functional programming and imperative programming? We'll be talking a lot about that, but let's start with again, by repeating what I already mentioned. Imperative programming relies on some simple device which can do simple commands. The mathematical model behind imperative programming is Turing machine. You know probably what Turing machine is. It's a simple device which can go read and write symbols from the tape, and it can be in different states. And depending on the symbol, it can switch to different states again. So it can do simple commands, reading, writing, and conditional branching. And those commands change the state of memory, change the state of tape in the case of Turing machine. Functional programming approaches problems from different standpoint. Like imagine you need to define what program does. Program is something which takes some input data and produces some output data. So the easiest way to reason about program mathematically is to use the term function. Function is something which takes input and produces output, right? But the way mathematicians think of functions is slightly not suitable for programming, because mathematical function is just a subset of Descartes' product. So it's basically the function is defined by the table of its values. On the contrary, if you want to reason about programming, you need to think about functions as compositions of simpler functions. So that is the way functional programming looks at the problem. If you want to do something, you think about it as a function which takes input data and produces output data. And this function is composed of simpler functions. And each of those simpler functions also takes input data and produces output data. So you don't have as such any memory or any state. What you have is the composition of functions which computes the result on the fly when you give it this result to the input. So that's the idea. By composing functions, you can break complex problem into simpler ones, and you can take a complex problem and decompose it until you reach the simplest possible operations, such as additions, multiplications, and so on. That is idea of functional programming. So let's start with an example. Suppose you want to calculate something mathematically, like, for example, this definite integral from 0 to pi of sine x dx. That is not something difficult to do. You probably would know how to write an algorithm for that. So this sine would look somehow like this. You need to break this interval into smaller parts, then approximate them by rectangles and compute this area, right? That's what you need to do for calculating the integral. So if you were to write the program in a traditional programming language, you would write something like this. You would take so-called accumulator. So accumulator would be a variable which will accumulate the result, and then you go by one. You would have several steps, and at each step you would calculate the area of each rectangle and add it to accumulator, right? So that would be the area, and it would be added to accumulator, and at the end it would accumulate the desired value. So why this approach is not very good? Well, in case of integral, it's probably not so bad, but if you think about real-world projects which have a lot of different variables and different places, it's very difficult to localize side effects, because every piece of program can change any other variable anywhere, and if you do it carelessly, you can easily get into trouble. And that is what happens. About 80% of errors in computer programs are caused by side effects, by somebody changing memory when you did not expect it to happen. And if you don't have variables, that problem kind of goes away. So let's try to think about this problem in the functional way. And to do it, let's think how can we solve this problem in Microsoft Excel. Not by using macros or something like that, but by using just Excel as a collection of cells. So probably you know that the way Excel works, let me switch to Excel, is that you can have a cell and then you can define another cell which takes the first cell and does some operation on it. For example, multiplies by 2. And if you adjust the first cell, the second cell also changes. So here you can see the where I'm getting, right? Excel defines functions on input data, and if I change input data, output data changes. And there is no way to define an accumulator. You cannot put a cell and then tell Excel to add values to it. It doesn't work like that. It just computes something based on other cells. So how can we compute integral in this case? Let's start with dividing the interval into, let's say, 15 points. And to do that, I will just number those points. Let me create 15 cells here with the numbers from 0 to 15, 16 cells. And then let me calculate, that would be I, and then let me calculate xi, so that x ranges from 0 to pi. So the way I do it is I will multiply this number by pi, let me take 3.14 for pi, and divide it by number of points, by 15. And I will make this formula to the whole, I will extrapolate the formula to the to all cells, right? So that's xi. Now let me compute sine of xi. It would be done in the same way, sine of this previous cell, and I can extrapolate it again. Then to calculate the area of each rectangle, I need to multiply sine by the length of interval of one small piece, right? Because I divided pi into 15 subintervals, I would need to take this value and multiply it by pi divided by 15, right? And again, let me extrapolate. So now this column contains areas of each individual rectangles, and to calculate the final integral, I just need to add them all together, right? And I get the result, which is almost 2, and the value should be 2 indeed. So that result is pretty much correct. Nice, isn't it? And I did not use the notion of accumulator here. So that is how a functional program looks like. It doesn't have variables, it doesn't have accumulator, it just has computations. Now let's get back to programming languages. We will definitely consider this problem once more at some point in the future. So if you look at programming languages, I mentioned that Fortran was the first programming language. And this is a kind of diagram which you cannot probably see very well. It lists all programming languages and how they depend on each other. And if you look here, you can see indeed there is Fortran on the top, but then there are a few other languages at the top which also do not depend on anything but themselves. And for example, one of those languages is Lisp. Here is Fortran, and here is Lisp. Lisp, as I mentioned, is one of the first functional programming languages. And there is one more language which starts from nowhere, which is Prolog, which is logic programming language. And there are other languages influenced by it. So you can see that those kind of languages, they are essentially different, right? They do not depend on each other. They do not take ideas from each other because they are based on different mathematical foundations. So here is the same diagram in a little bit more clarity. I put out all the traditional languages because you know all of them, like Java, JavaScript, and so on. They are somewhere here. And I just focused on functional and logic programming languages. So Lisp, as I mentioned, is the father of functional programming languages, and Lisp is kind of very old. It has very bracketly syntax with a lot of brackets. That's why it's quite difficult to use in real life, because you can get lost in brackets easily. And that's why there are different languages developed with slightly different syntax. And most notably, there is an ML family of languages, which is considered to be like very fruitful idea for how you can express functional programs. And from ML family, there were actually two big branches. One of them is relies on very pure functional programming with lazy evaluation, and I will tell you later on what it means. And this family ends up with a language called Haskell. Haskell is a very beautiful functional programming language. And another family is eager programming languages, which are kind of they are not as pure, they are easier to learn, and they are more applicable in the industry, so to say. And this road leads us to a language called F#. F# is the language that we will be using in our course. In terms of logic programming, you can see that there is Prolog, and Prolog influences some languages which are cross-functional between functional and logic. And language called Mercury is combines functional and logic programming features, and that's a really beautiful language, and we'll talk about it at some point in the future. And you can see that programming languages, they are quite different, and this beautiful picture tries to show characters of some of them. So, as I mentioned, different programming languages, they are based on different programming paradigms. By programming paradigm, I mean different ways of looking at the problem. And they also correspond to different mathematical foundations. So, as we already mentioned, imperative programming languages are based on Turing machines and von Neumann processor model and on simple commands. This is by no means a beautiful model. It's ugly from the mathematical point of view, because it starts with the real device, because Turing machine is kind of real device. It's not completely real because it uses infinite tape, but it was inspired by a device. So when you need to model a device mathematically, you end up with a lot of strange details, like you need the function which changes state, you need the state machine, and that is not a beautiful mathematical model. On the contrary, functional programming is based on very beautiful lambda-calculus. Lambda-calculus started as a mathematical notion, like a mathematical theory, and that's why the language which is built on top of it is also very beautiful and very pure. Logic programming languages, they are more complicated because as you can probably guess from the name, they are based on mathematical logic. And mathematical logic, if you take any rich logic like first order predicate logic, it's not computable. Like you cannot write a program which would tell you whether an expression in first order predicate logic is true or false. And that creates a problem. So that's why logic programming languages, they appeared later. They appeared like 10 years later than functional. And they need more mathematical theory to define what exactly is the kind of logic that is computable, and what exactly is the kind of logic which can be an algorithmic model behind those languages. So we'll talk about logic languages in the second part of our course. I need to mention that there are also some other paradigms, for example, situational or productional languages, and the most notable one is Refal. Refal is the language created in USSR. It's not like a language derived from standard international languages like Algol or COBOL, but it's completely different language based on production rules, on the rules which specify how do you take input and how do you substitute it with something else to get your job done. This algorithmic model is called normal Markov algorithms, and it is yet another model for describing computability. So, if we look at the history of programming languages, we can see that they evolve. Definitely, humankind tries to come up with the best programming language. And that's why those languages, somehow they are placed on this timeline, but they also placed vertically on another axis. And this vertical axis, it's hard to define what it means, but roughly it means how expressive the language is. Because, for example, in assembly language, you need to write a lot of simple commands to get your job done. In logic programming, for example, to get the symbolic differentiation done, you need to write a few lines, and the computer will figure out all the rest. So that allows us to say that it is, in a way, more expressive than assembly language, and even than C or C++. And that's why I kind of put those languages in some increasing order of expressiveness. And you can see here that I denoted I showed the difference between logic programming languages, functional languages, and traditional languages. And it just so happens that logic programming languages are, by chance, a little bit more expressive than imperative. But that is a little bit subjective, because I did not define any strict rules for expressiveness. So there are questions arise from this. For example, why is it not possible to create just one programming language which would cover all paradigms and which would be the best? And in fact, there were attempts to do that. I was in Microsoft Research Summit in, I think, 2004, when they were announcing a language called C Omega. And the idea behind C Omega was to combine imperative programming with functional programming and with relational database access. That was experimental language and ended up to be LINQ. In C#, you probably know that LINQ is a kind of functional core inside C#, which allows to do a lot of computations functionally, but it doesn't make C# a functional language, because it still contains variables, loops, and so on. It makes C# multi-paradigm language because it has a lot of functional features. And the same is true with many other languages. But it's not possible to build a completely cross-paradigm language, because they rely on different mathematical foundations, and that's why they are intrinsically different. Another question which arises is whether it's possible to build the most expressive language which would be super easy to deal with. And it comes back to the idea of Turing test, and whether it would be possible to develop a program where we just tell computer what to do and it does everything. In fact, logic programming languages, they appeared as a result of this research, of the research of automatic program generation, but it is definitely still not there. And in the logic programming part of the course, we will discuss in more detail why it's not possible, why it's not easy to do that, and what are the main barriers. But yeah, that is an interesting question, like how more expressive, how more beautiful, how more elegant programming languages might be in the future. So programming languages, of course, there are popular programming languages, there are less popular programming languages, and the good way to measure this popularity is by looking at different data on internet. For example, how many times the language is mentioned on Stack Overflow, how many repositories GitHub contains with this language, and so on. And there are a few indexes that are calculated based on those combined data. One of them is so-called Taiobe Programming Community Index, which is based on community interaction. In this index, functional programming languages, they are reasonably popular. Nowadays, probably the numbers have changed, because this is of, I think, 1 year ago. But the idea is the order of magnitude is still the same. The functional programming languages, they gain popularity lately because they are so good for developing parallel systems, for developing clean code with less errors. So the interest in functional programming raises with time. And that is why I think it's absolutely essential that everybody who wants to be in software development in this area needs to learn about functional programming. Absolutely essential. We would be using mostly the language called F# in our course. What is the reason for that? Well, the main reason for that is that F# is very applicable in real life. Like you can, if you are doing any .NET development, you can take any part of your project and replace it by F# because it's completely compatible with .NET platform, and you can easily call F# from .NET and vice versa. It is by no means a vendor locked up language, because you can use F# anywhere with .NET, and .NET Core runs on many operating systems. So you can easily run F# on Windows, on Mac OS, on Linux. You can run it in the cloud, you can develop web applications, you can develop console applications, you can develop data processing applications in Jupyter notebooks, and even you can develop the software for simple microcontrollers. I used to give a demo by programming a robot in F#, a robot to follow a line in F#. So if you take all modern functional programming languages, I think the major ones are 4 of them. F#, Haskell. As I mentioned, Haskell is the most beautiful functional programming language. There is also Scala, which comes from Java community. And there is also traditional Lisp. Lisp is not very modern because I think it's quite difficult to develop in Lisp, but Lisp is also very beautiful in the other way. So I think if you want to learn the best and the most beautiful and most difficult programming language, you should probably go for Haskell, and we will cover some ideas from Haskell later in the course, definitely. But for practical reasons, F# is a very good choice because it's beautiful, it's easy to learn, it's applicable to real life, and it is interoperable with all .NET ecosystem. Scala is also quite a nice choice if you do some projects in Java, but in terms of beauty of the language, Scala is less beautiful because it is based a lot on Java. I mean syntactically. The idea of Scala is that we take Java and we enhance it with a lot of functionality, a lot of functionlessness, not functionality, but a lot of functional features. F# on the contrary took a syntax of a functional language. It took the syntax of ML, so that's why it doesn't look familiar. You would not be tempted to program in F# in the same way you normally write in C#, for example. You would have to learn a new syntax, and that is probably easier if you learn new concepts as well. Unfortunately, F# is not purely functional. It means that it's possible to program in F# in traditional way. Like it's possible to write a loop in F#. It's possible to use mutable variables, but you should avoid doing that and learn the beauty of functional programming by restricting yourself to only functional features of F#. So how you can use F# in practice? F# has the site fsharp.org. It is the site of F# Software Foundation, and this site has the section called Use, and it describes how to use F# on different operating systems. So the best way is just to go there, select which operating system you have, and it would have all the details listed there. In short, to repeat what's written there, one of the easiest way to start is to use Visual Studio Code with .NET and F# compiler installed, and Ionite plugin. So VS Code with Ionite plugin converts your VS Code into a beautiful integrated development environment with a lot of functionality, like it would give you a lot of hints, autocomplete, typing information, and so on. So that is one good choice. Another good choice, and probably even easier, is to take the Visual Studio, the big Visual Studio 2019 or whatever version you have, because Visual Studio has the F# support built in. If you did not disable it specifically during installation, you would have F# installed. You just start using it right out of the box. One more way is to use .NET Interactive. .NET Interactive is the feature which allows you to use .NET family of languages inside Jupyter notebooks. If you learned Python, if you tried to do some data science, you know what Jupyter notebooks are. It's a beautiful way to combine executable code with some descriptions, with the text, and with visualization results. It is a tool that all data scientists use to process data in Python. And it's a browser-based tool. So you can easily install F# support for Jupyter notebooks locally on your own machine. Or you can also do it online in tools like Binder. Binder is an online free system which allows you to start Jupyter notebooks online. And it can support different languages. So the easiest way to experience it is to start with the course repository for this course and launch it in Binder. So course repository, the address is listed here, is github.com/schwarz/funkpro, and I will show you how you can launch it in Binder. So here is the repository itself. It contains already some examples of code, which I will be showing later on in the lecture. And to run the code, you just click here on Launch Binder. It takes you to a different site. And what happens here is that it creates a Docker container with all required environment, with the F# runtime, with Jupyter runtime. it happens. Sometimes it can take longer, but now because I have already instantiated this container a few times, it has the cached version, so it does it pretty fast. So now you have the notebook environment online and you can start using it. The only drawback here is that Binder can time out from time to time. So sometimes you may end up not using it for 15 minutes, and then you would see that your program is gone, because if the environment shuts down, there is no way to recover it back. So that's why it's not the most convenient way to use it, but you can definitely play with the code from lectures in this manner. So let me show you how you can do it. Just go to course, and this is the first notebook with introductory code. And here you can see the beauty of Jupyter. You have the text describing what goes on, and you have code. Let me clear all output. And here you can just click on the cell, click run, and you would see the result. Sometimes it takes a little bit of time to compute. Yeah, so you see, square root of 4 is 2. That's the way to use F# from the browser. Yeah, to show you the beauty of F#, here is, for example, the way you can compute the integral which we talked about earlier. I will not go into detail now. That is something we will be talking about later on during the course, when we talk about lists, about sequences, and so on. So let's sum up the main ideas of functional programming. So first of all, when we deal with a problem, we consider it to be a function which takes some input parameters and produces some output. This function is defined as a composition, composition of simpler functions, and each simpler function behaves in the same way. It takes data from input and produces some output. It doesn't have any hidden state, any hidden variables. So whenever you have a function, if you pass the same input, it would always give you the same output. This is something called stateless function, or pure function, because it is pure in a way that there are no side effects. Nothing happens inside the function besides the computation which is intended to happen. So, and it also means that there are no variables which can change their value. And also another important thing is functions are first-class citizens. You can consider functions to be values. You can pass functions to other functions, and that actually brings us a lot of beauty to function composition, because you can compose functions in very complex ways by doing operations on functions, and that brings power to functional programming. What else is important to know? As I already said, it's based on the sound mathematical theory called lambda-calculus, and the way program is executed is by step-by-step simplification. So we take the program. The program is a big mathematical lambda expression, and then we simplify it, and by simplifying it, we finally arrive at the result. The fact that there are no variables means that there are no side effects. It also means that it's possible to parallelize computations, because the function does not depend on anything outside. You can compute each function in parallel. Well, it doesn't mean that F# contains built-in parallelization, because if you just start computing everything in parallel, it would slow things down. It would not speed up, because there would be a lot of computational overhead. But functional code is much more easily parallelizable. And it definitely contains less bugs, because you do not have, as I mentioned, side effects. It's also close to mathematics, and it means that you can reason about programs. You can say, here is my piece of program, and it corresponds to this mathematical function. You can never do it in the traditional program, because in the traditional program, the result of the function can change during execution. And that's why there is no easy notion about that in mathematics. Of course, you can model all side effects, but it becomes ugly mathematics. In functional programming, it's beautiful mathematics, and much easier than in imperative programming. So let's start by talking about the main concepts of lambda calculus. In fact, this beautiful theory is based on just two mathematical concepts: abstraction and application. So what it is? Abstraction is when you apply function to an argument. So for example, you have the function plus, and you can apply it to an argument 1 and 2 and get the result 3. We can write it in F# as 1 plus 2, or we can also write plus 1, 2 to be more explicit, that plus is a function and 1 and 2 are arguments. So this is application. It takes function and argument and produces the result. And there is also the reverse operation, which is called abstraction. Abstraction is defined by using, in mathematical theory, it's defined by using lambda syntax, and that's why it's called lambda-calculus. The story here is that Alonzo Church wanted to denote it in a different way. He wanted to denote it by writing something x plus 2 and putting hat above x. And because it was not possible to typeset x at that time with a hat, because typesetting in the beginning of 20th century was really primitive and rudimentary, they proposed him that the easiest way would be just to use the lambda as the hat. And that's why this syntax, this slightly difficult syntax came about. So the idea of abstraction is that I can take an expression, for example, I can take an expression x plus 2, and I can make a function out of it. By writing lambda x plus 2, this expression becomes a function which adds 2 to any number. So you see the idea that if you just write x plus 2 in mathematics, it's not clear what it means. Do you want to compute it with a certain value of x? Do you mean it's a function? Do you mean it's an equation? If I write, for example, y equals x plus 2, is it a function? Is it an equation? What it is? In lambda calculus, it's perfectly clear that if I want to produce a function, which means adding 2 to any number, I write lambda x plus 2. X plays the role of a placeholder. It doesn't matter what the name x is. You can put any name here. It would not change the meaning. So you can imagine that if you have an abstraction, it produces the function out of expression. And then you can apply this function to something else and get make application. So for example, if I take this idea of lambda x plus 2 and I apply it to 1, how can I do it? I need to compute this expression x plus 2, substituting 1 instead of x. So that would be a simplification step. I take this complex expression and I simplify it to be equal 1 plus 2. This is called beta reduction, and we will hear about it in a moment. However, sometimes in programming we want to define functions, right? We want to give them a name. In pure lambda calculus, there is no way to give a name to a function because there are no names. And pure lambda calculus is just about simplifying big lambda expressions. And in the pure lambda calculus, functional program would be just one big lambda expression, similar to the factorial that I showed you in the beginning. A lot of strange symbols. In programming, we want to make things simpler. So, for example, consider this application, lambda x plus 2 applied to 1. I probably want to name the function lambda x plus 2 by giving it a name, for example, add2. In F# I can write it like this. I can say let add2 equals to fun x plus 2 in add2 1. So I always need to say, well, not always, but when I define add2 to be equal to something, it has certain scope. So this scope means that this substitution would make sense in some expression. In this case, in this expression, add2 applied to 1. And what it essentially means is that I can substitute this add2 by the value and get the lambda expression which I can then simplify. So it's not defining a variable which can change. That's why the title of the slide says let variables which do not vary. You cannot change the value of the variable. It's just the way to substitute a piece of code by a name, right? To make it easier, like it's not probably clear how to write add2 equals to fun x plus 2. It looks like a long piece of code. So that's why for programmers it's easier to write it in the equivalent way, but which is easier. Let add2 of x equals x plus 2, which looks like the normal function, like you would define the function, for example, in Python or something like that. Well, even in Python it would be even more complex. So it's a very clear way to define a function. What also is important here is that you can use application instead of let. It's a bit tricky now, and probably you don't have to understand it from the first try. But what the expression let x equals x per in E, what it means is that I can write the lambda abstraction function of x into E and apply it to expression, because when you simplify it, the expression would be substituted for x inside E. And that is exactly what this line means. I want to substitute x for x per inside E. So this let is a syntax sugar. That's what I mean to say. It's a syntax sugar which is on top of abstraction and application. Now let's come back to the idea of simplification of expressions. This simplification is called reduction because it reduces the expression, it makes it shorter. Let's take an example. Let's take this lambda expression, lambda z z1, lambda x x plus 2. So what does it mean? It looks quite strange, right? So what it means here is that this first lambda term here, it means take a function z as an argument and apply it to a number 1, right? So what this expression means, I want to take this function and apply it to the number 1. How do I do it? To do it, I do very simple reduction step, which is called beta reduction. From this expression, I produce the next one. The way I do it is I take this first expression z applied to 1, and I substitute this bracket for z, which give me lambda xx plus 2 applied to 1. And now I do the same rule again. I take expression x plus 2, and I substitute x for 1, and I end up having 1 plus 2, and this can be reduced to 3. So that's the way the functional program is computed. If you write the same thing in F#, the thing on the right is F# code. It is working F# code. So you can take it, you can paste it into Jupyter and execute it, and it will work. It will work by giving you the result 3. And the way it is computed is shown here on the slide. A more complicated example. Let's consider this ugly expression. So let's try to figure out what it means. I suggest that you make a pause now and try to figure out the result by yourself and then compare the result. And I will come back to the result in a second. So first of all, let's try to figure out the meaning. So what this construction here means, f of x, it means I want to take the function f and apply it twice to the value of x, right? So what I mean here by this expression is that I want to take the function lambda z z squared, the function of squaring something, and I want to apply it twice to the value 3. So I want to compute 3 squared squared. That would be the result. So how do I arrive to this result? Well, I do substitution from left to right. The first application to abstraction is this one, correct? So here I need to substitute this function for the value of f. So this is how I write it. I want to substitute f by lambda z z squared in the expression lambda x f of x. So I end up with this lambda x, and then the first f becomes lambda z z squared. Then the second f becomes another lambda z z squared, and then I want to apply it to x and apply everything to 3. Now I end up with another lambda abstraction on x. So what I need to do here, I need to substitute x by 3. And that is pretty easy. I have lambda z z squared applied to 3. Now I have 2 lambda abstractions, and I can go different ways. For example, I can take the thing inside the brackets. I can take lambda z z3 and apply it to 3, and it would give me lambda z z squared applied to 3 squared. And then another application, I get 3 squared squared, which is the result. I could also go another route here. I can make this whole bracket be reduced, right? I might substitute this bracket for z here. Try to do it and make sure that you arrive at the same result. Try to do it yourself, and on the next lecture we will discuss why is it the case. Do you always arrive at the same result if you go to different routes of computation or not? That's interesting piece of theory which we need to know. Now let's come back to programming. You are probably bored with mathematics and you want to start writing some things in code. Let's switch to notebook and see some code examples. So let me start by showing you that application and abstractions work. The example that we have already seen, I take the abstraction f of x, that applying function 2 times, apply it to the function which multiplies any number by 2, and apply it to 1. If I execute this, I should get the result 4. Now, to use let here, we can define this function f of x and give it the name repeat2, and function of multiplying by 2 twice. And we can define it either using this lambda expression. Fun f is called lambda expression, or we can do it using more traditional syntax. You can say repeat2 f of x equals to f of x, and twice x equals 6 times 2, and compute repeat2 of twice of 1 and get the same result 4. What's important here, I never specified type for any argument, right? Does it mean that F# is untyped language? No, F# is strongly typed language. So for example, if I say y.1.0 here, I get the type error, because F# figured out that this 2 here is integer, and that's why the function twice takes integer and gives back integer. So if I say 2.0 here, that would make things work correctly, right? Let me change it back to integer because that's something I want further in my code. Now, I said that complex problems are composition of simpler functions, right? What does it mean to compose functions together? Let's talk about that. Suppose I want to apply the function twice 2 times. In the normal life, if I were in C#, I would write something like that. I would say twice of 2, right? And you can write the same thing in F# as well. But as you noticed already, in F#, application is not denoted by squares, so you can omit squares here. You can just say twice of 2 like this. However, you cannot omit other brackets, because this would give typing error. Why would it happen? Because twice of x would be computed from left to right. All expressions are computed from left to right, and that's why when I say twice of 2, brackets are grouped like this, and that gives me a typing error. So you should get used to this kind of strange bracketing in F#, where you need to bracket successive applications. This is not convenient to write a lot of brackets, and that's why F# has even better syntax called pipelines. You can say I want to take 2, pass it as an argument to twice, and then pass the result to twice again, and this gives me the same result 8. Instead of that, I can also think about function composition. I can say let me take function twice and compose it with another function twice. This kind of sign means that I want to take 2 functions and build a composition and apply this composition to the number 2, and that would give me 8. Of course, you can also build the composition in the different direction, and it would give the same result in this case, but if the functions were different, it would give me different result. And I can even write interesting things like this. I take 2, give it as an argument to twice, and then give the result to another twice, which is kind of funny way to write the same thing. Now, when I mentioned application and abstraction, I said always that function can have one parameter, because it's always lambda x and some expression, right? You cannot say lambda and then many variables. How do I define functions with many arguments? Definitely, I want to do that. You can do it in 2 ways. One way is to use tuples. All modern programming languages have some notion of tuples, which means pairs or 3 items, those groups of 3 items, and so on. So I can use tuple as an argument. If I say let plus of a comma b equals a plus b, it means that function plus accepts one argument, which is a tuple of two numbers, which is kind of the same as two arguments. And that's one of the way you can do it. But there is also another way you can do it in a more beautiful manner. You can say let plus ab equals a plus b, and it would give me also 3. And I call the function now without any square brackets. I just say plus 1, 2. What does it mean? I said when you write something, it is computed from left to right. So if I say plus 1, 2, I should be able to put brackets in this way and get the same result, 3. And in fact, it works. And that's pretty strange. I mean, how can this be? The plus is a function, and how can I say plus 1 and then expect this to work? Well, that's quite interesting. Let me explain it in a little bit more detail. So when I write plus ab equals a plus b, what I'm in fact writing, I'm writing this: plus equals function of a, which is function of b, which is a plus b. And this is the same. I can also call it plus 1, 2 and get the same result, 3. So if I try to apply better reduction here, if I want to apply this plus to a number 1, for example, what happens here is that I take this right hand side and I substitute a by 1, right? So plus 1 would be this function, 1 plus b, right? And I can send plus 1, 2, and it would give me the result 3. So in fact, if I apply this strange function to one argument, I get function as a result. Let me show it one more time. If I leave the function in this way and I apply it to just to number 1, the result is function. This means that it's a function and not a number. Do you remember that I said that functions are first-class citizens? You can assign functions to variables and so on. So that's why you can say let p1 equals plus 1 and then call p1 of 2 to get the result. And even you don't have to define the function plus. You can use the built-in plus operator. You can say p1 equals plus of 1, and that's one of the reasons you can write plus in this manner, plus and then arguments. You can omit argument and get a function if you do partial application. This is called partial application. You apply the function to some arguments and not all of them. And this gives you the function which you can apply to the rest of the arguments to get the value. So now I have the good challenge for you. Try to define the following functions: 2x, 2x plus 1, and 2 times x plus 1. And you can of course do them using lambda expression, like easily, very easily, right? But also try to do it without lambda expressions. Try to build them as compositions of other functions. For example, 2 times x, we already know this function is called twice and we already built it above. But how do you define 2x plus 1 without writing an expression? By composition of the idea of multiplying by 2 and adding 1. And by the way, 2x you can also define without lambda. Let me show you how to do that. You probably know it. You can, instead of writing let twice x equals x times 2, you can say let twice equals times 2, and that would be the same. It's just duplicate definition, so I remove the first one, and that is correct. You see how beautiful it is. You can write functions without specifying arguments. So now try to do that with the rest of those functions. Let's come back to the idea of typing. Lambda-calculus itself, when you write lambda x plus 1, is untyped theory, meaning that we do not consider variable to have any kind of type. And that's why sometimes it's possible to write crazy things in lambda-calculus. For example, lambda z, 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 lambda z, z, z. That is correct lambda-calculus expression. But in terms of common sense, it doesn't mean anything, because you cannot have a function which is applicable to itself, right? It's nonsense. So that's why programming languages like F# and ML, they extend lambda calculus with typing. So the idea here is that, for example, when I define the function +1 of x equals x plus 1, F# looks at 1. It understands that 1 is integer, and that's why +1 is assumed to have type from integer to integer. It's a functional type. If you write something like +xy equals x plus y, type here is more tricky. Let's first start with this one, when you pass tuple as an argument. So if I pass tuple as an argument to function, then the input type of the function is this one, int times int to int. Int times int means Descartes' product, right? Like this in mathematics. Now, if I write it in this form, which is called carried form. Haskell Curry is the mathematician whose first name Haskell is used as a programming language, and Curry is used as the notion of carrying. Carrying means writing function of many arguments by many functions of just one argument. So this is called carried form, and this is called uncarried. So if I write the carried form of the function, so what it means, when I pass this function an integer, it gives me back the function from integer to integer. So if you put brackets, you should put brackets here in this way, and always when you write type expressions, you should write brackets from right to left. That is the default. Like this is the way people assume brackets to be put. So, but yeah, so it's normally written just int to int to int, and it means that int is the final result and it has two integer arguments. Another interesting thing, if you write something like this is also perfectly valid F# expression. So let f0 of f equals f of 0. It means take any function and apply it to 0. So what would be the type of this f0? It takes one argument, which is a function, and this function takes integer as an argument, right? But it can produce anything else. So it can be, for example, a function which adds 1 to a number. It can be a function which converts number to string, for example, in which case it would take number 0 and produce string 0. So that's why this type of this f0 is complex. It takes a function from integer to any type t, and produces the result of this type t. This is called polymorphism. F# has a very rich polymorphic type system. When I say type system consists of the following. It has some base types, like for example integers, floats, strings, and so on. And then it has some type constructors, like for any two types t1 and t2, you can build a functional type from t1 to t2. For example, from int to string, you can build the function which converts integer to string, and it would be a functional type. Then it has the tuple type. You have already seen it. It groups two types together. Like if you want to have the name of a person and his social security number, it would be a tuple of string and integer. And then there is one more clever thing which is called direct sum or union type, which is denoted in algebra by plus, and in F# we will see the notation in a moment. And the union type means that it's either one or the other. In C, the corresponding analog is union. And this type is really heavily used in functional programming, and we will see the example of using this type in a second. So what it gives us, in fact, this type system gives us the ability to construct complex types which are called algebraic data types. We will definitely revisit this notion more times during the course, and the idea why they are called algebraic data types is because they are constructed from union types, which is kind of plus, and from tuples, which is kind of multiplication, and this union type can correspond to a kind of polynomial expression, and that's why it's called algebraic. Let's switch to example. Suppose I want to solve a quadratic equation. How would I do it? And during this example we will see many features of F# as the programming language. So probably if I want to solve a quadratic equation, I will define a function solve. And we have already seen how to define a function of many arguments. So I would say let solve ABC equals. Then what I want to do first, I want to compute the discriminant, right? So I would say let D equals B squared minus 4AC. This would be like inner let. And then I compute the roots. x1 minus b plus square root of d, and x2 is minus b minus square root of d divided by 2a. And I return tuple. So if I run this on some equation, like x squared plus 2x minus 3, it gives me two roots, 1 and minus 3, which is kind of cool. It gives me back the tuple. And I can say if I want to return them back into some kind of variables, I can say let x1, x2 equals to solve 1 to 3. And then I can print, for example, x1 plus x2 just to verify via theorem. But what happens if the equation has no solution? What do you think would happen? Would there be an exception? No, in fact, F# is built in such a way that it produces so-called not a number. When it cannot compute something, it gives you back not a number. But there could be some other problems, like if you divide by 0, it would give you back an error, division by 0, an exception. In functional programming, normally you do not want to have exceptions. You want the function to return and indicate that the error happened. That's the way you normally do it. So how we can do it in our case? Well, not a good way to do it, but one of the possibilities is to denote some kind of special tuple as an error tuple, right? We can even say, for example, let error equals this, and then if there is an error, then I return error. And you can see, indeed, yeah, 1, 2, 3, which is an equation which doesn't have solutions, gives me back this kind of error tuple. But this is definitely a very bad way to do it. What happens if I pass the correct coefficients which give me back those kind of roots? It would be indistinguishable from error. So that's why it would be nice to have the way to distinguish between correct result and error. Well, it would also be nice to be able to distinguish between cases when there are two roots and when there is just one root. For example, if I pass a equals to 0, it means that it's not a quadratic equation. It's a linear equation and it has one root. So to consider all those cases, what I can do, I can define the specific return type, which is a union type. This is how union types are defined in F#. So let me comment here. It's a union type, which would be float times float plus float plus so-called unit type. So, but how does it look in F#? I say Q result, this is the name of the type, is either quad of float times float, so this is the first option, two roots, or it's linear of float. So when I say linear, I expect one argument, or it's no roots. No roots means no arguments. So now the solve function would look like this. I say solve ABC. If a equals to 0, then I return one linear root minus c divided by b. Otherwise, I compute the discriminant. If the discriminant is negative, I return no roots. If everything is good, I compute x1 and x2, and I return quad of x1, x2. So if I run this, in this case, I get no roots. If I run 1, 2, minus 3, I get my tuple. If I run 0, 2, 3, I get just one item. So I get the result. The type of the result is not just integer. It's not just, it's not just float. It's complex type. So to do something with it, for example, here if I say printf, I want to print the result, you would see that this is linear 1.5. And if the equation is solvable, it's quad of 1, 3. It's not just 1, 3. And I cannot say here let x1, x2 equals to this, because that would be a typing error. So what I can say here, if I'm sure that the result has roots, I can do something like this. But that would not always work. It would only work if the equation is solvable. If it's not, it would give me an error. So the way to deal with those complex typing is to use pattern matching. So what pattern matching is that you can match on different types of option type, of union type. So, for example, I can define a function print. I can say I print the result, and to do that I match the result with the following. I can say with no roots I want to print no roots. When it's linear I can want to print linear. When it's two roots, when the two roots are equal, you see I can also add some additional conditional operators here. In this case I would print x1 equals x2 equals to the value. And if two roots are different, then I would print x1 equals something, x2 equals something. So you see this would nicely work, indeed. 2y minus 3, and it prints me the roots. So that's the way you normally would handle errors or different results. There is one more beautiful syntax which I want to show you, which is called function syntax. Function is the same kind of keyword as fun. It's a lambda expression. But this lambda expression supports pattern matching built into it. So I can say, for example, let print equals to function, and then I can specify all different options. Like if the input is no roots, then I want to print no roots. If it's quad, I want to print two roots, and so on. So it's exactly the same pattern matching operator as above, but condensed into just one lambda expression. And it works in the same manner. So what we have seen here, we've seen pattern matching, we have seen conditional operator if. By the way, I did not say explicitly that we will study now conditional operator, but we have seen how it works. And we've seen algebraic data types. Pattern matching is a very powerful construction. For example, if I want to model a domain of people with their documents, I can say the documents is either social security number with integer number or passport with its number as a string. And I can define the person which would have name, passport, age, integer, and the document. And so on. I can then match this person using different kind of pattern matching. So pattern matching is also very powerful. You can have patterns, you can have when conditionals. And instead of patterns, you can say underscore. Underscore means always. So instead of writing if you want, for example, to write conditional with 3 possible branches, then you can write something like match D with, and then you can say one condition when D is greater than 0, when D equals to 0, and then the third one would be the catcher, like in all other cases, do the third one. So pattern matching is cool. That's the main idea of this slide. And then again, I want to say that in F#, for some reason, there are 2 constructions for lambda expressions. One of them is fun, another one is function. They are very similar, and if the function has just one simple argument, you can use any of them. But fun supports multiple arguments. You can say fun xy instead of writing fun x, fun y. You can just say fun xy. So it supports carrying and multiple arguments, but no pattern matching. Function supports only single argument, possibly tuple, and it supports pattern matching. Like if you want pattern matching, you use function. Why do we need those 2 kind of constructions? Because the syntax of the language becomes more concise, like this. Now let's come back to the idea of loops. We definitely want, when we write programs, we definitely want something to repeat many times, which means loops. But in functional programming, there are no variables, so you cannot have traditional loop. So the only way to imitate the loop is to use recursion, right? So you should not normally think of the problem as a loop, but you should think of the problem as of a recursive function. So for example, if you think of factorial, do not start thinking like, to calculate a factorial, I need an accumulator and I need to multiply it by 1, 2, 3, 4, 5. Think about factorial like the definition, like factorial of 1 is 1, factorial of any x greater than 1 is x times factorial x minus 1. And you can write this using pattern matching, right? You see how beautiful the factorial definition is here. You can say factorial is a function which for 1 returns 1, for any other x returns x times fact x minus 1. And that would work. So let's start again talking about loops. Let me add a few things here. Let me show you how you can define loops. Suppose I want to do something very simple. I want to print numbers from 1 to 10, right? So how to do that? I would do that by defining a function print from a to b. And then how would it work? If a is less than b or less than equal to b, then I should print a, right? Then I print a. Printf is a nice function. Printf is very similar to the C version of printf. You have the format string and arguments. But the good thing about printf in F# is that it's typed. You know, like if I say %d, it means that argument should be integer and it would not work on any other argument. It's very clever typing. But in this case, I say %d of a, and then I printed the first number. Now I need to do the recursive call for the rest. So I say print a plus 1 b, and I want to call it on print 110. Here there is one problem. You see it says type check error, the value is not a function, because print, it cannot be defined inside of itself. Because normally, like if you have a name, F# is trying to resolve it. If the function is recursive, I need to specify it explicitly by saying let rec. It might sound a little bit ugly, right? Why do I need to specify explicitly? Why cannot compiler figure out by itself that the function is recursive? Well, in some point next time when we discuss how recursion is handled in lambda-calculus, you would see the beauty of this. Because recursion is essentially very different between let rec, the semantics of let rec, and normal let. They are different, and we want to state this explicitly. So this would work. This would print numbers from 1 to 10. So whenever you want to do something, something loopy, when you have loops, you would have to write a recursive function. But not always. What you can do here, you can in fact factor out the operation, right? Because normally you might want not to print numbers. You might want to, for example, go through all the numbers and do something else. So you can, the idea that you print something, you can factor out of this function. So for example, I can call this function let rec my for, that would be for loop. It would go from a to b and it would accept the function f, which tells what to do. And instead of printf, I would just say f of a here. And instead of print, I would say my for from a plus 1 to b function f. And here I would say my for from 1 to 10, and what to do for I print f %di, and that would be sorry, fun I, of course, like this. So you see we have developed the analog of for loop. And when I say there are no loops in functional programming, I meant it. It's not a loop. You cannot, for example, add all numbers from 1 to 10 using this loop, right? You can only execute a function on any number, on 1, on 2, on 3, on 4, and this function can only do something, and that's it. It cannot return a value, it cannot accumulate those values. We need to develop different loop if we want to accumulate something. It's just a syntax sugar for recursive function, but it looks like it's for operator. So if I want to print something in a loop, I know how to do it. And by the way, this can be simplified. Remember, we talked about partial application. Here I have a function which accepts two arguments, the string and integer. So if I want to omit this, it would give me a function. So I can simplify this and write it like this. for all numbers from 1 to 10, print, and I don't have to specify the name of variable. See how beautiful it is. Now let me consider another problem. Suppose I want to compute something more difficult, and that would be an easy example, but still, let's compute e to the power of x using Taylor series. You know that function can be represented as Taylor series, an infinite series, and for e to the power of x, it looks like this. So it would be 1 plus x squared divided by 2 factorial, and so on, and arbitrary term would be x to the power of n divided by n factorial. So how do I calculate that? Suppose I just want a few first numbers of the series, like first 5 terms. It looks like I need to define the function to calculate factorial, right? How do I do that? Yeah, I can say factorial of n. It's the same definition as I described above. Then I need a function to compute the power. I would say power of x equals to function. So the second argument is the power. If the power is 0, I return 1. If the power is not 0, then I take x to the power of n minus 1 and multiply by x, right? And this should be should return float, not integer. And then the final function, my exp. My exp need to calculate how many steps to take, right? So that's why I call it not my x, but my x prime. My x prime of x would take x and the number of terms. For example, 5. So here, if we start with 5, how do we compute the function? If we count back to 0, I return 1. Right? It means that I end up with the first term. If it's n, I compute the nth term, x to the power n divided by factorial of n. And here I need to convert factorial to float explicitly, because otherwise it's strong typing. It would give me integer, and I cannot divide float by integer. So I compute this, and I compute my exp of x with argument n minus 1. This computes the first n minus 1 term, and I add nth term, right? And then to compute my x value, I compute my x prime of x and 5, which means take 5 terms. I hope that's more or less clear. Now let's execute it, and it doesn't work because I mixed typing. I need to make sure that the function returns floating point, right? What is wrong now? Not clear. To me, what is wrong now? This is because I made the stupidest mistake. I forgot to put rec here in all functions. Now it's much better. This is just because I wrote fact n, but n should not be here. N is the argument of function. Now it's good. Now my e, so e to the power 1 should be equal to e, which is 2.7, which is good. So this looks pretty neat, right? If I were to write it using C#, I would probably write the same functions, and the same functions would take more space, but not much more space. So right now I did not do anything conceptually different from C#. Well, of course in C# I would use loops, for loops, and that would be, it would be not recursion, and probably you can argue that loops are better. And in the next lecture we will discuss why it is not the case, why tail recursion can be the same as loops, and how you should write recursive functions in such a way that they are not in any way worse than loops. But it still feels like I did not do anything interesting. Now let's do something interesting. So you can see that all those functions, they look pretty much the same, right? They have recursion, they have the end of recursion, they repeat n times. So this idea of repeating n times can be encapsulated into another function. I would call it iter. So how would it work? I would say I want to iterate from a to b, right? So the number n would iterate from a to b. I want to apply function f each time. and I want to start with the initial value of I. So, for example, if I want to compute the factorial, I want to start with 1, and I want to multiply it by 2, and the result multiplied by 3, and the result multiplied by 4. So the idea of multiply would be this function f. The idea of I want to start with 1 would be this I, and from 1 to 10 would be here, right? So how it works, I say if a is more than b, then I return I, which a is more than b means I finished my computations, like, right? So I return I. If it's not, what I do, I compute the function f, I apply it to a is the current number, and I compute the rest, like I compute the rest of the function from a plus 1 to b. So, for example, if I want to compute the sum of numbers from 1 to 10, I would do it like this. I would say iter, and then I would pass it a function which contains x and accumulator, and I say I want to add x to accumulator. I want to start with 0, I want to go from 1 to 100. So this is the sum of numbers from 1 to 100. I can simplify this, because here you can see the idea of fun x and accumulator. It doesn't really matter that variables are called x and accumulator. I can call them whatever. And I can even get rid of them altogether, because the idea here is that I want to take two numbers and add them together. And this can be described by the function plus. So I would say that the function sum from a to b equals to iter plus 0 a to b. And that would work. I define the function sum, which adds all numbers from a to b. And I can even omit a and b, because remember, partial application. And this would also work. You see how beautiful. I defined the very abstract function, and I defined the sum based on this abstract function. Let's see what else I can define based on this abstract function. Of course, I can define factorial. I can say factorial equals to iter times 1, 1. And then there would be n, which is removed due to partial application. So this is factorial. You see, just one line of code gives me factorial. Can I define power x to the power of n using the same function? Indeed, I can. I can say let power of x would be iter, which takes in this case a number. This number goes from 1 to n, but I don't need it. I need to multiply by x all the time, right? So that's why I put underscore here. Underscore is the kind of variable which is not used. I can put any number t here, that would be the same. But normally, if you want to emphasize that this variable is not used, you put underscore. So I'd say function of underscore and accumulator, and it would multiply accumulator by x. So this would happen n times. I want to start with 1 point, because power is now, it's not integer function, it's the floating point function. And you see, we are here seeing another case of polymorphism, right? Depending on the type of the function changes. So I want to start with the floating point 1, and I want to go from 0 to n, because x to the power 0 should be 1. I should not do it any single time. Okay. And then I can define the function myexp in the same manner, right? So what is myexp? Myexp, I want to add to accumulator the nth term. Here is the nth term. And I want to go starting from 1 to 5. And those 3 lines of code give me the definition of E. You see, instead of writing this bulk of code, I just ended up with 3 lines of code which rely on the more abstract concept. Right? That's the idea of functional programming. You see, in functional programming, you want to factor out the ideas. You never want to stay with the idea that you can do something in recursive manner. In fact, you would almost never use recursion by itself. You define clever functions which are recursive, and then you assemble your problem from them. And we will see a lot of functions which allow you to do that. I mean, functions which process lists can do that, and we will definitely learn how to do that. Now, let's finish the lecture with some nice example, inspiring example, and that would be computing Mandelbrot set. Mandelbrot set is a fractal which looks like this. So how can we compute it? How does it define? How is it defined? So in fact, the way it's defined is the following. So suppose this is a complex plane. So real numbers and imaginary numbers. And each dot inside the fractal is the complex number, right? So this is some complex number C. And for each dot, we need to figure out whether this number is inside the fractal or not. What I will do now, I will not focus on colors. I would just draw black and white fractal. So I basically need to be able to say whether a dot is belongs to the fractal or does not belong to the fractal. So how do I define that? I consider an infinite series. The series would look like this. The first number in the series, z. Let me write here. So the first number z0 would be equal to 0, and then all the rest z n would be equal to z n minus 1 squared plus c. So for each c, I would compute this infinite series. So for example, if c equals to 0, I would get 0, 0, 0, 0, 0. This is a very beautiful series because it's converging. It's also bound. Now, if I take c equals to 1, it would become 0, 1, 1 squared plus 1, 2, 2 squared plus 1, 5, and so on. So it would be diverging series and also not bound. And if I take c equals to I, so the point somewhere here, or actually rather somewhere here, if I take c equals to I, it would give me 0, I, then I squared would be minus 1 plus I, and then if I take minus 1 plus I squared, I would get some complicated number, but it would be another series. So I want to take all those points for which the series is bound, right, and that would be Mandelbrot set. For the sake of simplicity, I cannot operate on infinite series because I would need infinitely long time. So I would just say, let me take first 20 numbers, and I want to plot those points for which 20th value of the series is relatively small. Let's say less than 1. So bound inside 1. So that would be my set, which is very similar to Mandelbrot, and this is the set I will plot. It is not exactly Mandelbrot set, but very close. So let's see how can we do that. So to do that, first of all, we need to operate on complex numbers. And luckily, F# is based on .NET. In .NET, we have .NET numerics, system numerics. It's called the namespace, and we can operate on complex numbers easily. But to do that, I need to specify type here, because F# is a little bit limited in such a way that if I don't specify the type in the arithmetic function, it would assume integer. Like if I say the function is equal to x plus 1, it's easy because 1 is integer and F# knows the type. But if I say, for example, a plus b, F# does not know the type of a and b, and that's why it cannot figure out the type immediately. We will come back to this later on, because there are ways to write polymorphic functions like this, but if you just define a function, it will not be polymorphic, and F# would assume typing to be integer just because integer is such a beautiful type for programmers. So that's why I need to specify the type of at least one variable. So if I say here that z is complex, for example, and I define z squared plus c, it would give me a function from complex to complex to complex. Now I need to be able to compute the 20th term in the series, right? I need to be able to compute 20 times, apply this function 20 times. So to do that, let me define another function which would repeat any function n times. It would compute f of f of f of f of x n times. How do I do that? Well, I can define it using recursion. That would be like an exercise for you. You can try to do it. There are a few ways to do it, but try to do it yourself. That would be a nice and simple exercise. But I will do it in a more tricky way. I would use the same function iter. Remember our function iter. Iter we used to compute like factorial, or x to the power n. X to the power of n is the best example, because x to the power of n is the same as f to the power of n. But in case of f to the power of n, I don't multiply numbers, I build function composition, right? And the idea of power is the same. So how do I apply iter here? I take, in the beginning, I take the identity function. This is called identity function, which maps from x to x, right? And then each time I need to compose it with the function f, right? So I take accumulator t, and I return the composition of f and t. This is the composition operator, which we have seen earlier. And then I repeat it from 1 to n times, right? Just to, as a sanity check, I want to repeat 8 times times 2 and apply it to 1. It would give me 256, which is correct. Now, to plot the set, as I mentioned, we need a function which would tell me whether it's the point is inside Mandelbrot set or not. So the way I do it is the following. I say, let me start with the Mandelbrot function. The Mandelbrot function is a function of 2 arguments, c and z. I want to fix c, right? And for this c, I want to study how the sequence behaves. So if I fix c, if I apply Mandel to c, it gives me back the function from complex to complex, right? And this function I can pass to repeat. I say I want to repeat 20 times the composition of this function, right? So I would compute this. I would make 20 steps like this, and then I apply it to 0, to complex 0, and I make sure that the absolute value is less than 1, and it gives me back the boolean, right? So is Mandel of c takes any complex number c, it builds it inside the function, then applies this function 20 times, and then applies it to 0 and checks that it's less than 1. I can of course build this using some additional let for clarity, but I think that's pretty clear like this. I hope it's understandable how it works. And now what I'm left to do, I just need to print the fractal. So how to print the fractal? I can just do for loops. And this is our Mandelbrot set, right? You see how beautiful. Well, you can see that I'm cheating. I'm using for loops. Well, F# has for loops. I mentioned that F# is the multi-paradigm language. So it does have traditional for loops. But I don't have to use traditional for loops here. I can use also my own for loops, which I defined above. I think they were called my for. I can say my for from 0 to, I don't remember how many lines, to 20. My for from 0 to 20, and that would be function of I. And then it would be my for from 0 to 60, and that would be function of j. And then I need to make sure to end that at the appropriate place. And that is the same. You see, I completely avoided loops. So it means that loops are not essential, like specific syntax for loops does not break, in this case, the functional purity. But that does not look exactly very beautiful, right? You would say that we probably want to more beautiful thing. Let me switch to Visual Studio and show you how F# works in Visual Studio, because Visual Studio supports full .NET. Notebooks might not support some libraries, and to add them it requires some additional engineering effort. Visual Studio supports full .NET. In .NET there are many libraries to deal with graphical things, right? For example, there is System.Drawing and Windows Forms. So what I can do here, I can build the same loops, but for the image. Can take the image 400 by 400 pixels, and then using for loops, I would build each pixel inside the image. I would compute whether it's inside Mandelbrot set or not, and if it's inside the set, then I put the black dot, otherwise I put white dot in the bitmap. And then I show this bitmap in the window. I build Windows form. I add I add the function which is called each time the window is drawn, and then I show this window. So to execute this whole program, so let me show you. In Visual Studio, I can also execute F# step by step. For example, I can select those few lines of code, press Alt Enter, and this code would be executed below here in F# Interactive. And this has some advantages because I can immediately see the typing. For example, this is the typing for our repeat function, from integer to arbitrary function from A to A. And here is the Mandel-F, which is from complex to complex to complex. And here are the rest of the functions. And finally, this bit. You see, it opens the window, and here is our Mandelbrot set in the full beauty, right? So I think that's pretty impressive, right? If we were doing this in any other language, I mean, it would not be that concise, because we would have to like have a loop, and then inside the loop we need to be checking whether the sequence is bound or not. Here is just a few compositions of functions. I think that's impressive. So, final thoughts, like why do you need to learn functional programming? Traditionally, the first functional programming language was Lisp. And if it is so good, why it is not so popular? The reason for that is the following. Like Lisp was extremely slow language. Because at that time, languages were very primitive. Like even C. C requires memory allocation by hand. It does not have garbage collector. Lisp had garbage collector. And at that time, that was really slow. So that's why Lisp was used by researchers and not in the industry. So you can say that originally when functional programming languages came about, they were more expressive. And the main thing of them is that they required more thinking than writing. Because, for example, in the example with e to the power of x, you would be able to write for loops very easily. I mean, that's not rocket science. You can write for loops. And you don't have to think about that. But you have to think how to factor out the idea of iteration, how to build this into a function. It is a little bit more tricky. But this is rewarded because you have just one place where you can make error. You have just one function with iteration, and all the rest relies on it. If you want to parallelize it, you parallelize just this function. So it's definitely much better, but it's more complicated. People who know how to use functional programming, they are more educated. You cannot just take the high school student and ask him to start programming in Haskell or in F#. So that's why for industry, that's a drawback. You need more qualified developer. And you have less performant code because of garbage collector. Lisp, I think, was one of the first languages with garbage collection. But as the positive thing, you have no side effects and you have much less bugs and you have more expressive language and more beautiful language. So it was kind of, so-so. Two pros, two cons. But what happens now? Now those languages become as performant as imperative. Because, for example, F# is based on .NET platform. And code compiled by F# is almost the same as code compiled by C#. There are a few minor drawbacks because of partial application, but they are really minor, and the code is optimized, so it's almost as fast as C#. It doesn't really matter what you write. So this bad performance is a myth. It's no longer the case. And also parallelism becomes more important, because back at those times when functional languages appeared, there was only one processor, right? One core. Now processors are multi-core, and it's essential to be able to write parallel programs. And it's very difficult to write parallel programs because of multiple threads conflicting with each other. Functional programming solves that to some extent. And that's why it becomes now much more popular. And there are many functional languages which are now used mainstream. For example, one of the biggest examples is Apache Spark. If you consider big data solutions, like big data when you need to process loads and loads of data distributed across clusters. This system is written in Scala, in a functional language, specifically because it's easy to parallelize things if it's written in Scala. As I mentioned, LINQ inside C#, all modern languages have a lot of functional features, including C++ and C#. And there are a lot of examples of software, including big software written in functional languages. I mean, the first known example is probably AutoCAD. AutoCAD was written mostly in Lisp. Emacs editor was written in Lisp, and back at that time it was slower compared to other editors, but right now it's almost the same. Inside Microsoft, many things, including F# compiler, driver code verification kit inside Windows SDK. Many things use functional languages. So, for the course, if you speak Russian, you can use my book, Functional Programming in F#, and the course would be pretty close to it. It would be definitely more advanced because the course is more theoretical and the book is more practical. But just to learn functional programming, it's a good start because it's very concise. It does not discuss imperative features of F#, because other books which are translated to Russian, they tend to go more into language syntax and not into concepts. So this book is specifically written to be concise, so it's pretty small. The second part of the book is already a little bit outdated, but all the main things are the same. There are many other books available either in Russian or in English, and you can find some of them online. I want to encourage you to have a look at some books on Lisp and on Haskell, because that would definitely broaden your horizon, and we will also discuss Haskell in a little bit towards the end of the course, and we will probably not discuss Lisp so much. So that's good reading to try to figure out how Lisp works as well. So those are the sources for the course, and I hope you are inspired to learn functional programming. If you have questions, why do I need to learn it? Would I be happier if I learn functional programming? If you want to talk about that, let's get together online and do that, because definitely you would get happier if you learn functional programming, and that's why it's very good that you start doing it now. What we will learn during this course, we will learn principles of functional programming. We will also touch a little bit on lambda-calculus. I think we have already started that a little bit, but we will go a little bit deeper on mathematical theory behind it. We will also touch the interesting branch of mathematics called category theory, which allows us to think about programming, about composing systems in a slightly different way. We'll talk about semantics of programming languages and implementation of functional languages, and of course also consider some practical tasks such as data analysis, machine learning. We'll see a little bit how functional languages can be used for that. And that concludes the first lecture of this course. I'm looking forward to hearing you in our seminars, and have great functional programming course.